Well, hello, everybody. I'm John Linford. I work for ARM, and I'm joined here by Dr. Shinji who works for Fujitsu. And today we're going to be talking about SVE, the scalable vector extension for ARM architectures, and how you can use SVE with HPC workloads. The outline of our talk today, I'll give about a 12-minute introduction to SVE, describing what HPC is, what SVE is, and why they work well together. And then Shinji will take over and give you a presentation about the Fujitsu compiler and the software environment you find on the A64FX. And then we'll provide a case study of how you can optimize Stream, a popular memory bandwidth benchmark for the A64FX using the Fujitsu compiler and their software environment. So let's get started by talking about SVE and high-performance computing. So first, I want to sort of level set about high-performance computing, because HPC means a lot of different things to a lot of different people. Some people call these systems supercomputers, some people call them data centers. When I'm talking about HPC, I'm talking about a highly coupled yet very flexible platform for solving some of the most challenging problems that we have today. So the idea is that we have leadership class computing systems with hundreds or thousands, maybe even millions of CPU cores, with record-setting network characteristics that often consume many megawatts of power. These are massive computers. And the key distinction between a supercomputer or HPC system and a data center is that your supercomputer can operate as a single system and bring all the computing power available in that system to bear against one problem at a time. Data centers tend to be more scalable, where the idea is to serve many users simultaneously and provide a large throughput for a great number of jobs. Supercomputers tend to have very few jobs, maybe even just one job running on all of the hundreds of thousands or even millions of cores. And they're typically used to address problems in aerospace, medicine, anything that really requires a scientist to be able to gaze into the intricate parts of a problem and come back with knowledge that couldn't otherwise be achieved without that supercomputing resource. So one example of a supercomputer is the Fugaku supercomputer, which is based at Japan's RIKEN supercomputing center. This is currently the fastest supercomputer in the world, according to the HPL benchmark, which is a high-performance LENPAC, a sort of linear algebra benchmark. And it's also a very energy-efficient architecture. Fujitsu's A64FX CPU, which I'll discuss in detail in a moment, provides very good high performance efficiency. So not only is this supercomputer the fastest in the world by certain measures, the system is also among the most energy efficient in the world. This is a highly desirable characteristic for supercomputers because the power bills to maintain these can be quite large. And so the more you can save on the power, the more you can do, the more science you can do, with less overhead costs. Now, the Fujitsu A64FX, this is the first CPU to implement the scalable vector extension. It's a custom ARM design by Fujitsu, so it implements the ARM instruction set architecture, but the microarchitecture is completely Fujitsu's. It implements SVE at 512 bits and consists of a cluster of 4 core memory groups, or CMGs. Each CMG has 12 cores plus 1 helper core to run the operating system, and provides 8 gigabytes of high bandwidth memory, or HBM. Now that combination of vectors with high bandwidth memory is characteristic of supercomputers and is really where the A64FX derives its compute power, being able to provide high amounts of memory bandwidth to a very wide vector engine. The Fugaku supercomputer is composed of many, many nodes built on the A64FX CPU, where each node has 1 socket of the A64FX, 2 nodes per blade, and the whole thing is water-cooled. So now I want to talk a little bit about SVE, ARM's vector instruction set architecture for scalable HPC computing. Now, SVE is unique because it implements a vector length agnostic programming approach. Unlike most vector instruction set architectures that define the width of your vector register in the architecture itself, SVE does not define the width of the architecture. That is left up to the CPU implementer. And it can be anything from 128 bits up to 2048 bits. Now this enables a new programming paradigm, a completely new way of going about vector programming called vector length agnostic programming. SVE is not an extension of Neon. If you're familiar with the ARM instruction set architecture and Neon, you might know that Neon is a fixed width architecture defined for 64 bits or 128 bits. SVE is not defined for any number of bits except for between 128 and 2048. And it also brings new features to the instruction set that allow us to tackle traditional barriers to auto-vectorization, specialized instructions that make it possible to vectorize codes that normally wouldn't vectorize with a fixed width architecture like Neon or SSE or AVX2. Now, like I said, SVE does not mandate a single fixed vector length. It can be anything from 128 bits up to 2048 bits. The A64FX happens to implement 512 bits, but that was a decision made by Fujitsu in their architecture. It could be anything between the 128 and 2K bits. And the exact same binary code can run on any vector length between 128 and 2K. This means that there's no need to recompile your code if you're moving between different vector widths. It will scale up or scale down as necessary. And it also means that the programmer needs to take a vector length agnostic programming approach. You cannot consider the number of bits in the architecture while you're writing your code. Instead, you use VLA and a concept of predicate registers, which I'll describe in a minute, to dynamically operate on the concept of vectors without caring about how wide exactly they are. So for example, if the easiest way I think to see vector length agnosticism is to do a mental experiment. Imagine you needed to compute data which has 10 chunks of 8 bytes. With a scalar architecture, you would have one loop which iterates over an 8-byte register for 10 iterations. So this is 10 little shot glasses of data. Now you might accelerate that with a fixed width vector instruction set architecture like Neon at 128 bits. Using 128-bit Neon, I can do 4 iterations of a vector loop that uses Neon instructions to process as much of the data as will fit nicely into a multiple of the vector width, and then have a scalar drain loop, which operates on the last 2 chunks of the 8-byte data. So 2 loops using 2 different instruction set architectures. Vector length agnostic architectures like SVE allow you to use just one loop, and in the last iteration, which would typically have to be a drain loop at a fixed width architecture, you use predicates to adjust the width of the vector down to fit the remaining data. So the first, if you imagine a certain vector width here, your first 2 iterations are of a certain size. They consume as much of the data as possible. And then whatever the remainder is, you just predicate to put the remainder of that data into the vector register and use one loop for all the data. You don't have a drain loop at all. It's just one. Now, in addition to being vector length, load and scatter store instructions that allow you to vectorize non-contiguous memory access patterns, and also has extended floating point horizontal reductions. So especially for graphics processing, you'll find that if you want to do a pixel averaging kernel, you can use special instructions with SVE to rapidly compute the averages or sums across vectors. Now, a key question is, if I don't know how many bits are in my vector register, how can I program that? How do I chunk up data? How do I perform iterations? The key to programming in vector length agnostic SVE is predicate registers. Predicates allow you to map vector operations onto lanes of the SVE vector. You also can do predicate arithmetic to determine how wide your vector is and how you should stride over the data. So in the first case, if we use per-lane predication, we can take specific mathematical operations and map them onto vector lanes. And you can do this in a very rich way. You can map, for example, the first 3 lanes of the vector, every 3rd lane of the vector. You could map by some series of lanes in the vector until you have filled the vector. There's a very complex set of instructions for predication. You can also use predicates to drive loops. So you may find you can use a predicate to ask for which elements of this vector is I less than n, for example. And this is how you can iterate up to the last elements of your array and dynamically resize the SVE vector, in a sense, for the last iteration. SVE also has this powerful feature called software managed speculation. So you can do a first faulting load instruction that allows you to process vector data right up to the edge of protected memory. And this allows you to vectorize things like strlen and memcopy even can be vectorized with SVE. Now, let's walk through how would you actually count by the width of your SVE vector in a real code. So if I don't know how many elements are in my vector, which I don't, and even if I know the hardware vector bit width, I should ignore that because I'm using vector length agnostic programming. You have to assume that you don't know the width of the vector. So there are special instructions that allow you to dynamically query the characteristics of SVE at runtime. This incw instruction, for example, says increment the integer x4 register by the number of 32-bit lanes. That's the W's for word for 32-bit. The number of 32-bit lanes that will fit in a vector. So this is how we can increment and stride over data by vector width, is by using special SVE instructions that count by vector width. Similarly, if you don't know the vector length until runtime, how do you initialize constants? There are special instructions like index and ptrue, you see them here, that allow you to generate sequences or series of numbers that fit into your vector. For instance, I can use the index instruction to say, fill my SVE vector zb.s with integers beginning from number 1 and incrementing by 4 until the vector is full. I can also use instructions like ptrue to say, initialize my vector with multiples of 3 with values of true in multiples of 3. So I get true, 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 until there's not enough space for a triple of true. And the remainder, in this case, would be false, false, because you don't have enough space for a triple of true. So there's a rich set of these instructions. If you need to see the exact details, please see the ARM architecture reference manual. There's not enough time to go into the details here. But this should be your first go-to source of information for the instructions that are available in SVE and how to use them. And I want to emphasize again that SVE is not Neon. It's a different instruction set architecture completely. It is vector length agnostic. Neon is a fixed width architecture. And SVE is really optimized for HPC, not for media. It supports wider vectors than Neon, and it also provides new instructions such as gather, load, scatter, store that allow you to vectorize more effectively very complex codes. So at this point, I'd like to turn over the talk to Dr. Shinji Sumimoto, who will give us an overview of the Fujitsu compiler for A64FX systems and introduce a case.
Thank you, John. Hello, everyone. My name is Shinji Sumimoto. The next topic is an overview of Fujitsu compiler for A64FX systems. So, here is a picture of the Fujitsu compiler system architecture. Fujitsu compiler includes some language, Fortran, C, C++, OpenAP in the internal, usually some instruction level parallelization and loop level optimization, but also provides internal communication core array and API, and also provide a mass library for internals for the SSL2, BLAS, LA-Pack, SSL2, Scala Pack, and FFT, and also have a tool for IADE and debugger and profilers. So, Fujitsu has been developing a supercomputer for 40 years. since the development of the Fujitsu supercomputer, Fujitsu has been developing some compiler tools. And A64FX also provide features and compiler approaches, and also for over 40 years. So A64FX also inherits the feature of K-Computer and Prime HPC FX100. It's the form of our product, Spark base. And at the same time, such kind of compiler usage is usability, including options and programming model, are inherited. For the hardware perspective, compiler targeted now 5 trillion-bit wide vectorization to promote optimization, such as constant folding and fixing vector lengths. But also, Fujitsu compiler provides vectorization as vector length agonics and neon also supported. So below the table is since the development, the advances from the K-Computer and the FX100 and Fugaku. And almost different of the ARM chip instruction architecture, but almost same feature as provided and enhanced. So now I'm talking about some Fujitsu compiler language standard support. C11, C++14, Fortran 2008, and OpenAP 4.0 are fully supported. And additional C++17, Fortran 2018, OpenAP 4.5, OpenAP 5.0 are partially supported. So let's talk about optimization of the compiler. So there are two important optimizations to accelerate performance. Number one is vectorization. It's automatic vectorization is enhanced to the utilize SVE, and also OpenAP shimmed directory and HLA are also available. Second thing is software pipelining. This technique improves instruction level parallelism of loops and fission. Loop fission is dividing in the single loop to multiple loops. The techniques also reduce the necessary registers in order to promote software pipelining. So, here is a picture of the Fujitsu compiler optimization flow. There is a 5 stages of compiler stages. The first one is vectorizing loops with SVE instructions. And the second one is loop fission, reduce the required resources if needed. In this figure, the second, below the center of the figure, the single loop will divide into 2 loops. And the third stage is software pipelining. And fourth stage is register allocated with optimization. And finally, the 5 stages of pre, post, IDE instruction scheduling is performed. So let's talk about some of Fujitsu compiler command. Fujitsu compiler provides own compiler and also provides a cross compiler. For the ARM CPU, it is relatively slower than Scala power, the relative than IEs. So we provide interactive for cross compiler. It is much faster than compile time and reducing time. And almost command and options are almost same, but the only difference is for the cross compiler, it's a suffix px. That's only. So let's recommended option because Fujitsu compiler has so many options to detail optimize. So I talk about some recommended option. That means -k first option is recommended for performance. So when we set the -k options, there the table shows a default turn on that so several things. So first one is -03, and second one is -k data alignment, and -k eval, and some constant folding, and so many things. And another notable option is performance. I'd like to show you. So options will promote control optimization is first minus k pre x. This is in code which is important through the loops before entering loops. And second minus k is 2. It's a vectorized loops which contains if constraints with prediction. And minus k OCL, it is an enable optimization of the control language. That is a Fujitsu specific directive to control optimization. And second part is parallelization options. Minus k parallel apply automatic parallelization. And second one is minus k OpenMP that enable OpenMP directives. And third one is OpenMP with SIMD. And third one is use option to know how apply the optimization. And minus k listen t that output compilation optimization information in the this file. That's a suffix to LSC in the source code each. And also a k-opt message is useful to its output the optimization of the message. So next topic is the optimization of the A64FX by Fujitsu compiler. At this time, I took the stream benchmark. It is a very, very well-known basic benchmark for the basic combination of computation and memory access benchmark. Stream consists of 4 benchmarks: copy, scale, add, and triad. And I took the stream triad. It is the most memory-intensive one. And below the two picture is a basic source code of the stream triad benchmark. It's very simple and easy. And you can see the left below the picture. In the middle of the picture, you can see the minus programmer, OMP parallel 4. And the next line is the for loop. And it's very easy to recognize such kind of loops. A matrices equal B matrices plus scalar multiplies C matrix. It's very easy. And below the right figure is a definition of the each matrix. It's defined static. So how to optimize the stream triad performance? So utilize maximum memory bandwidth and computation. There are very important 3 topics. Number 1, boosting memory prefetch access. Number 2, boosting shift operation. Number 3, it's very important, but removing extra memory access. For example, extra memory prefetch operation, and next one is needless memory read access. So we think about the 3 kind of topics. So we took some 4 set of compiler options. Number 1 in the table, it's a basic optimization at minus 03, minus k.a.a. and SVE, and ARM8, and OpenMP. Second one, option set is 1 plus memory bandwidth option. That means minus k assume equal memory bandwidth. Third one is almost same as number 2, but different from the use directory and Z field and software prefetch operation. I talk next slide. And fourth one, option set is the same as number 3, but eliminating a loop unrolling. So let's talk about Z field option. Z field option is eliminating needless memory access. Usually, memory write access needs the memory data before writing, because the processor uses cache line technique. And Z field eliminates extra memory read, which is completely replaced in cache line. So it's such kind of read does not need memory access. So the XFX Z field use DCZB instruction to eliminate needless read access. I can show the below the figures. So in the upper case of the figure, when Z field not used. So stream triad is a 3 kinds of set of matrices can be accessed. And these are B and C matrices and write A matrices that are minimally needed. But before the writing of A matrices, there need A matrices before writing. So it needs 4 streams. However, number 2, when Z will used, so Z will action, maybe this Z will instruction is performed. The zero fluid cache line is prepared in L2 cache. And read memory, the reading some A matrices provided by L2 cache and does not need memory access. And it also display with the hardware prefetch. So we use a software prefetch instead of the hardware prefetch. So in this case, it's reduced to 3 streams. So approximately including a 25 memory bandwidth upper bias. So what is the result? So number 1. So there are each option set and number 1, 4, and 12, and 48 thread. In the number 1, it's a one thread performance most better, 72 gigabytes per second. However, for a 48 thread, it achieved 629 gigabytes per second. And using a memory bandwidth option, one thread performance is not so good, but the 48 plus 850 gigabytes per second. And third one, instead of some Z-field and software prefetch, it increases up to the 848 gigabytes per second. And number 4 option, without unloading option, are slightly faster than that of number 3. This is my end of frame. So could you back to the John?
Thanks very much, Shinji. So I wanted to invite you to try some SVE examples and hands-on materials yourself. We have a set of training materials at the URL shown here, and these include slides, source code, and worked examples that will walk you through different tool chains and different SVE programming cases. Now, 2 important things to note about this. First, if you don't have access to a system with SVE in your hardware, these hands-on examples include instructions for using the ARM instruction emulator, or ARME, to run the SVE examples on any ARM platform, even if SVE is not available. So this is a good way for you to get started with the tool chains and the environments, start porting some code and verifying the accuracy of the port ahead of silicon availability. There's also worked examples here for the ARM compilers, libraries, and tools, the ARM Alenia Studio, which we didn't have time to show today. But in addition to the Fujitsu compiler and libraries, there are other software environments to support SVE, like the ARM Alenia Studio that I just mentioned, and also your standard GCC and LLVM compilers support SVE. So these hands-on examples will walk you through using SVE with GCC, LLVM, and ARM, as well as the materials that you've seen here from Shinji. So in conclusion, we've shown you SVE, we've shown you how it's implemented in the A64FX, and we've introduced the Fujitsu compiler for programming SVE on the A64FX, which in my opinion is probably the best software environment you can get for the chip. ARM is definitely new to HPC, but we're gaining a lot of momentum in the space, in part because of intellectual property like SVE being designed from first principles to address problems in that space. And we're seeing SVE as a powerful new technology for addressing problems in not only HPC, but also artificial intelligence, machine learning, and even wider areas where really challenging problems start to present and vectors can be brought to bear on those problems. So I want to conclude and say thank you very much for attending our presentation. And that's it.